Now, this is a very simple, in fact, a question which is framed in a very subtle way, but is very interesting in terms of its concept. And we'll try to solve this question using equations of motion, conservation of mechanical energy, and work energy theorem. Now, most of the books that I refer have included this question in the chapter Motion in a Straight Line under the topic Motion under Gravity, which is which is actually the ideal thing to do because it really doesn't suit the kind of the genre of loss of motion or work energy power for that matter. But anyway, it's always better to explore multiple ways of looking at the question here, right? So so yes, first we'll do equations of motion, work energy theorem second, and then conservation of mechanical energy. Sorry for this wrong order. It doesn't matter here. Okay, so first and foremost, let's move with equations of motion, right? Why? Because we're doing motion in a straight line. To understand the question better, the tennis ball here is dropped from 9.8 meter, which means this height here, well, I should technically be taking this very correctly as 9.8 meter. It starts from rest. Sorry. Starts from rest. It will speed up slowly and will be very fast before hitting this ground. Hits the ground. Well, all of this takes place in a straight line. I've just taken 3 instances to make sure that we understand the point clearly. So it hits the ground, and when it hits, it undergoes some kind of deformation in the floor. Why? We'll come to it in a while. And after that deformation, it goes up. It was dropped from 9.8, but it goes only up to 5 meter. Now you might be wondering, since it's 5 meter here, wouldn't it be easy to do the calculation if it's 9.8? No, well actually it's more easier when you do it 9.8 because the multiplier becomes very easy. So the ball is dropped from 9.8 meter. It hits the ball, it squashes a little, then it bounces back up to height 5 meter, and all of this takes place. This takes place in 0.2 seconds. Or in other words, this reversal of velocity, which means it was coming down, it reverses its velocity direction, it goes up. This reversal takes place in 0.2 seconds. Okay, so the visualization of the given statement is clear, I hope. Okay, now if that much part makes sense, let us analyze each and every section of the problem given. Motion before hitting the floor. So the ball is being dropped, it reaches this point. To bring more clarity, I have dropped the point at which the ball is dropped, I have named it as A. When it touches the floor, the corresponding position as B, the velocities as VA and VB respectively. So initial position is A, VA, final is B and VB. Applying equations of motion, V square minus U square is equal to 2AS. Now what comes in? Yes, now comes the most important question here. Which sign convention to use? Well, usually in all the problems that I've done before this, I've chosen along the direction of motion as positive and against the direction of motion as negative. So I thought of going for the traditional convention method here, which is choosing an arbitrary direction to be positive and the opposite of that to be negative. So I have taken here that the downward okay, this shouldn't be confusing. I've taken here that the upward motion is positive and the downward motion is negative. So all the variables of the motion, if they are acting upwards, would be considered as positive. Correspondingly would be considered as negative. Does it make sense? We'll go through in detail. Velocity of the object is acting downwards. Velocity is acting downwards. Therefore, V is negative. Acceleration due to gravity, the force of gravity will always pull the objects towards it. That will also act downwards. And therefore, acceleration due to gravity, A is minus G here. Why minus G? Because acting downwards. Downward we are taking as negative. This is the initial position, final position. Displacement vector is from the initial to the final, which means displacement vector is also acting downwards. Therefore, S is also equal to negative. Okay. So if we pull this in, if we pull this in to the equation, S is negative, acceleration is minus 10, V is negative, minus V, U is negative, minus VA. Well, to be more precise, it should be minus VA. Now, what is VA? The value of VA is equal to 0. Why is it equal to 0? Because it is dropped from rest. So what we get is minus VB square is equal to 2 into minus 10 into minus 9.8. Now, I think the way I have written this would be a bit confusing because it should be minus VB, the whole square actually. Okay, minus VB, the whole square. So what we get is VB square is equal to VB square is equal to 2 times 10 is 20 times 9.8 is 196. Negative times negative is positive. So VB square is equal to 196. And therefore, VB here is equal to root of 196, which is 14 meter per second. So now you might be wondering, okay, because if it's going to be squared, then it doesn't matter positive or negative. It will be equal to positive. Then why are we concerned about the sign convention here? We are concerned about the sign convention because not all equations of motion has a square in it. V is equal to U plus AT has no square in it. Does that make sense? Think of it. Write it down. Talk to yourself. Now let's see what happens after the rebound. So the ball is going up now. I have defined this as initial position B, final C, the corresponding velocities as VC and VB respectively. Applying equations of motion, V square minus U square is equal to 2AS. Again, sign convention. Now, we'll have to stick to the same convention throughout the question, which means acting downwards is negative, acting upwards is positive. All the variables of motion which are acting downwards are taken as negative. All the variables of motion which are acting upwards are taken as positive. Okay, now let's see. The body is moving up, which means velocity is acting upwards and therefore velocity has to be considered to be positive. No matter what, acceleration due to gravity is acting downwards. Therefore, acceleration here will still be A is equal to minus G. Displacement vector is from the initial position to the final position, which means the initial position will have the base and the final position will have the head. Therefore, displacement vector will also be acting along the positive side. Positive. So displacement would be positive here. Okay. So bringing that in, we have displacement is positive, acceleration is negative, velocity is positive, initial velocity is VB positive. What is VC? Very important. See, VC is equal to 0. But it's not dropped from VC. Why should VC be equal to 0? Because why? Because at C, the ball comes, oops, is momentarily at rest. it is momentarily at rest at that point. So if you were to visualize this, if I drop the ball like this, it comes down here, it bounces up, it stays here for a second, and then it comes down again. Okay, one more time. A ball is dropped like this, it bounces up, it reaches the maximum height, it stays there for a second, and at that second, the ball is at rest. Okay. So since the ball is at rest at C, VC is equal to 0, which means VC this terms is equal to 0, and therefore minus VB square is equal to 2 into minus 10 into 5, which is VB square is equal to minus 100, and therefore plus VB is equal to 10 meter per second. Okay. Now, yes. Now I'm coming to it. You might feel some confusion regarding VC and VB. Let's try to understand that as well. Why do we assign direction later? What am I talking about? Assigning direction to velocity vectors later. Why? Velocity is a vector, so direction matters. But when velocity is squared, it is scalar. So direction information is lost. What are we talking about? We're talking about the idea that velocity, say v is equal to vx into I cap, for instance. What is v square? V square is actually the dot product of v and v dot v, which is vx I cap dot vx I cap, which is equal to vx into vx times I dot I, which is further equal to vx into vx is vx square. What is I dot I? It is I times cos of the angle between I and I, which is cos 0, because I is this vector. So 2I, the angle between two I vectors would be equal to theta is equal to 0. So cos 0 is 1, I into the magnitude of I is 1, magnitude of I is 1, so this becomes Vx square. So V, which was actually a vector, when squared becomes a scalar. So squaring of a vector results in the loss of the direction, the sense of direction. And therefore, we'll have to pull out that direction again. So when we calculate acceleration or change in velocity, we must bring the direction back. Why? Because acceleration is not a scalar and is a vector quantity. Falling down is taken as negative, as we have considered before, and up is considered as positive. Okay? So when the ball is moving downwards, before the impact, the velocity was positive meter per second. Oh, there is a mistake here. My bad, sorry. This would be taken as velocity coming down, which we consider as velocity at B. VB would be taken as minus 14 meter per second. Okay. And when the ball is going up, it will be taken as VC is equal to plus 10 meter per second. Impact. Okay. What? So this is before impact, and this here is after impact. Okay. Now, when we get this, velocity before impact is minus 14 meter per second. Velocity after is 10 meter per second. Therefore, change in velocity is final velocity minus initial velocity, which is 10 final minus initial minus 14. 10 minus 14 is 24 meter per second, and therefore average acceleration is delta v by delta t. Delta v is 24 meter per second. All of this happening in 0.2 seconds, so that becomes 24 meter per second. Let me just check for the consistency. 24 meter per second, which gives us 120 meter per second square. Okay. So yes, this understanding is really important here. sign convention and applying that to the upward and downward motion. Let's now look at the same question using the concept of work energy theorem.